Hello everyone. So welcome to the first hour of magnetism and matter. In this hour, we will talk about geomagnetism and about the behavior of a bar magnet. So without wasting time, let's start talking about geomagnetism. Now, geomagnetism is a simple topic given that you know what is the meaning of up, what is the meaning of down, what is the meaning of north, south, east and west. But before we talk about geomagnetism, let's understand these terminologies. So let's say this is our Earth, our beautiful Earth, and we know that Earth rotates about its axis from west to east, and we even know that this axis has a tilt of 23.5 degree. For the sake of understanding, as we are going to have one more axis, magnetic axis, I am going to keep this geographic axis straight everywhere. So do not think that the sir doesn't know that the geographic axis is at some angle. Sir knows it, but we need to talk further. So let's assume that the geographic axis is straight. Now this point on the geographic axis, the topmost point is called the North Pole and this point is called the South Pole. So the geographic axis passes through the geographic North Pole and the geographic South Pole. Now let's talk about what is the meaning of up, down, east, west, north and south. So first of all, let's understand what is the meaning of up. If there is a person standing somewhere on earth, then up means away from the center of earth. The direction moving in which you move away from the center of earth, that's called up. So this direction is up. What is the meaning of down? Down means towards the center of earth. So this direction is down. So away from the center of earth, up, towards the center of earth, down. Now let's think of another case. So this is earth, but rather than thinking of earth as earth, think of it as a solid sphere. Let's say there is somebody standing at the North Pole and there is someone standing at the South Pole. For these two people standing at the North Pole and South Pole, what will be the direction of up and down? So, removing earth and thinking of a solid sphere, we will say that for the person standing at the North Pole, up means away from the center of earth, down means towards the center of earth. Now do understand this down is not same as south. Down means towards the center of earth. Up means away from the center of earth. And for the person standing at the South Pole, up means away from the center of earth and down means towards the center of earth. So now students make these idiotic statements like, for the person standing at the South Pole, down is up and up is down. No. Beta, you should know what is the meaning of the definition of down and up. Up means away from the center of earth and down means towards the center of earth. Okay, then sir, what is the meaning of north, south, east and west? Beta, north, south, east and west are the direction in which we move on the plane of the earth. We know that earth is this curve, this is sphere. Here we have got North Pole, here we have got South Pole. If you are standing here, let's say on earth, the direction while moving along which you will reach the North Pole of earth is called the north direction. So for you standing here, north will be the direction that takes you towards the North Pole. What is south? South is the direction that takes you towards the South Pole. And this direction moving on the surface of earth inward will be your east, and this direction moving on the surface of earth outward will be your west. So this is how we define north, south, east, west. North, south, east, west are on the plane of the earth, while up and down are perpendicular to the surface of earth. Up means away from the surface of earth, down means towards the surface of earth. So if we think of earth, and let's say we think of a place on earth, let's say this place. Now for a person standing here, north is the direction that takes you towards the North Pole. So in which direction this person should move so as to reach the North Pole, that direction is north. South is the direction that takes you towards the South Pole. Earth is a sphere. So this direction keeps on curling as you keep on moving down from equator to the pole. So this is meaning of south. For a person, let's say standing here, along the surface of earth, this will be north. Along the surface of earth, this will be south. For a person standing here, along the surface of earth, this will be north. Along the surface of earth, this will be south. So north means the direction that takes you towards the North Pole, and south means the direction that takes you to the south pole. Do understand that north, south, east, west are along the surface of earth, parallel to the surface of earth, while up and down are perpendicular to the surface of earth. I am sitting in this room. Somebody asks me, what is up? I will say here. It means that perpendicular to the surface of earth. Down means here, perpendicular to the surface of earth. While north, south, east, west are parallel to the surface of earth. You need to understand this thing first. So, do understand, north, south, east, west are along the surface of earth, and up and down are perpendicular to the surface of earth at any place on earth. So without wasting time, let's now start understanding geomagnetism. So what type of magnetic field is produced by earth? If this is earth, we know that earth has got a geographic axis. For the purpose of understanding, I am drawing this geographic axis as straight. I know that it has got a tilt of 23.5 degree. Do not keep on thinking on that point. Now, we know that somewhere near the south pole, Earth's magnetic field lines come out of Earth and they enter the Earth somewhere near the north pole. So they come out somewhere near the south pole and they enter back into Earth somewhere near the north pole. Now, if we visualize these magnetic field lines, they come out from a place somewhere near the south pole and they enter at a place somewhere near the north pole. The place from where the magnetic field lines come out is called the south magnetic pole, and the place where the magnetic field lines enter is called the north magnetic pole. So here you have got something called north magnetic pole, there is something called south magnetic pole. Do understand that the north magnetic pole is nearby north pole and the south magnetic pole is nearby south pole. Now students usually get confused when they think of the theory given by Sir William Gilbert. Sir William Gilbert said that the Earth's magnetism is due to a huge bar magnet placed inside Earth. This huge bar magnet is placed in such a way that the north pole of this bar magnet is near the south pole and the south pole of this bar magnet is near the north pole. So the magnetic field line comes out of the north pole and enter into the south pole, and because of that Earth shows its magnetism. But we know as a matter of fact that at high temperature all bar magnets loses their magnetization. So this can't be the case. You can't have a humongous bar magnet placed inside Earth which is creating Earth's magnetic field. That's not possible. So hence there is no big bar magnet within the Earth. If assume that there is a big bar magnet present inside the Earth and that bar magnet is producing the magnetic field of Earth, then beta, the north pole of that bar magnet has to be near the south and the south pole of that bar magnet has to be near the north. But there is no such bar magnet. So we say this line joining the magnetic south pole and magnetic north pole as the magnetic axis. Okay, so there is something called geographic axis which joins the geographic north pole and geographic south pole. And then there is a magnetic axis that joins the magnetic north pole with the magnetic south pole, a straight line. Now, know that the exact reason of Earth's magnetic field is unknown. Nobody knows what's the actual reason that Earth has a magnetic field of its own. Many a time students are confused, so I will give you one method to remember it. Think of magnetic north pole. Think of magnetic north pole as the north pole of Earth as shown by a bar magnet. Think of magnetic north pole as the north pole of Earth as shown by a compass needle. Compass needles are used for navigation, yes. Why? Because they point towards north? No, they have got nothing to do with Earth's geographical north. Compass needles are nothing but magnetized material. When freely suspended, they point in direction of net magnetic field. Now, the compass needle points in the direction of magnetic north, not towards the actual north. So, understand that a compass needle points towards magnetic north pole, not towards the geographic north pole. Then, sir, since magnetic north pole and geographic north pole are two different points, does it hamper our navigation? Yes. And to overcome this particular problem, we have defined a term called declination, which I will talk about soon. So without wasting time, let's keep on learning geomagnetism. Now, we need to talk about Earth's magnetic field. We have talked about this that somewhere near the South Pole, geographic South Pole, Earth's magnetic field lines appear to come out of Earth. And somewhere near the North Pole, geographic North Pole, the Earth's magnetic field lines appear to enter into the Earth. Now, this place from where the magnetic field lines appear to come out of Earth, that is called magnetic South Pole. And this place where the Earth's magnetic field line appear to enter back into the Earth, this is called magnetic North Pole. Now, you need to remember these all points because they are important. The first point, at magnetic South Pole, the direction of magnetic field is up. Sir, why up? You need to understand the meaning of up and down, east, west, north and south. The direction up means away from the center of Earth. So at the magnetic South Pole, the magnetic field lines comes out of the surface of Earth. So at this point, if I ask you what is the direction of this magnetic field, you will say, sir, it is away from the center of Earth. Since the magnetic field is away from the center of Earth, the direction of Earth magnetic field is upwards. I want you to visualize it this way. If you are standing at magnetic South Pole, you won't know that you are standing at magnetic South Pole because it will be kind of the same. It's not that this person will fall down, right? So if you are standing at the magnetic South Pole, just the way you are sitting in your room somewhere in India, which has got a latitude of 23.5 degree approximately, and you don't feel that you are sliding down the Earth, right? Because the force applied by Earth on you is towards its center. So for you, this direction is up and this direction towards the center of Earth is down. Similarly, for a person standing here, they will feel that the Earth's magnetic field lines are in upward direction. If they hold a freely suspended bar magnet in their hand, the freely suspended bar magnet acts like a magnetic dipole and it will point in the direction of magnetic field due to Earth, so it will point in the upward direction. So if you take a bar magnet, tie a thread around it, and if you are standing at the magnetic South Pole, the bar magnet will point in the upward direction. You should know this. Now, bachcho, similarly, if you are standing at the magnetic North Pole, the magnetic field lines are going downwards. If you are standing here, you will say that down means towards the center of Earth, up means away from the center of Earth. So at magnetic North Pole, magnetic field is in the downward direction. So at magnetic South Pole, the direction of magnetic field is upwards. At magnetic North Pole, the direction of Earth's magnetic field is downward. Now let's say you are no ordinary human being, you are Superman. And if you run from the magnetic South Pole to the magnetic North Pole with a bar magnet in your hand, at the magnetic South Pole, the bar magnet will point upwards in the direction of Earth's magnetic field. At the magnetic North Pole, as you run from here to there, the bar magnet's direction of orientation will change and will become downward as you reach the magnetic North Pole. So at magnetic South Pole, when you are standing, the direction of Earth magnetic field is upward. So the freely suspended bar magnet will align in upward direction. As you run along the surface of Earth, you are Superman. You can even run over water. So as you run from magnetic South Pole to the magnetic North Pole, the alignment of this freely suspended bar magnet changes from upward direction into downward direction. Now, we need to understand that for any place in the southern hemisphere, your bar magnet will point above the horizontal. Just like we have got geographic equator, we have got something called magnetic equator. At magnetic equator, the bar magnet will point parallel to the surface of Earth. And once you are in northern hemisphere, then the bar magnet will point below the horizontal. So as you run from magnetic South Pole towards magnetic North Pole, the orientation of freely suspended bar magnet changes from upward to downward. In the entire southern hemisphere, the bar magnet points above the horizontal, and in the entire northern hemisphere, the bar magnet points below the horizontal, and at magnetic equator, the bar magnet is parallel to the surface of Earth. Now, We will say that in southern hemisphere, the direction of magnetic field lines is above the horizontal. So they are above the horizontal. In northern hemisphere, the direction of magnetic field is below the horizontal. Now, if in your childhood you have played with the compass, there was a time where in your compass box, your bottle, your bag, your shoes, everywhere, they will give you a compass. And I had many of them in my home. What is a compass? There is a horizontal dial, and the horizontal dial has a magnetic needle suspended at its center, and this whole system is encased inside a transparent fluid. Now, when I used to play with it in my childhood, I always used to find that the compass needle points below the horizontal. The north is always below the horizontal. And I used to think why this north always points below the horizontal. Why I can't make it horizontal. Never did I realize that I am living in India and India lies in the northern hemisphere. Since India lies in the northern hemisphere, the direction of magnetic field due to Earth is below the horizontal. As in the northern hemisphere, the direction of magnetic field due to Earth is below the horizontal. The freely suspended needle will always point below the horizontal. So now, at the magnetic equator, the Earth's magnetic field is horizontal. It means that it is parallel to the surface of Earth. Now we are going to talk about something called angle of dip. What is the angle of dip? The simple meaning is, as a child, when I was playing with a freely suspended bar magnet, I always found that this compass needle always points below the horizontal. And I did not knew about magnetism and physics behind it. But I always understood that it points below the horizontal. Now let's say this is the horizontal level, and the compass needle points below the horizontal. It points below the horizontal because the Earth's magnetic field is in this direction, because we were living in India, which lies in the northern hemisphere. I have never been to any part below the equator. I always wanted to visit Australia or New Zealand so that I can see a compass needle pointing above the horizontal. After pandemic, hope so that I will be able to do this. So in the southern hemisphere, the Earth's magnetic field are moving above the horizontal. In the northern hemisphere, they are moving towards below the horizontal, and that's why the compass needle points so. Now we need to understand that the entire development of science has taken in the northern hemisphere. So whether you think of UK or USA or Germany or Spain or any country which has worked on science, they all lie in the northern hemisphere. And all the physicists always saw the compass needle to point below the horizontal. And they always knew that there is a dip in the needle. Hence, they defined a term called angle of dip. What is the meaning of angle of dip? The dip taken by the compass needle with the horizontal. That's called the angle of dip. And why the compass needle takes a dip? Because this is the direction of Earth's magnetic field. So, we say that the angle made by Earth's magnetic field with the horizontal is called angle of dip. The angle made by Earth's magnetic field with the horizontal is called angle of dip. Now it's called angle of dip. It's not called angle of rise. Why it's called angle of dip? Because there is history involved. The entire development of science took place in the northern hemisphere, and in the northern hemisphere the Earth's magnetic field lines appear to go below the horizontal. That's why the magnetic needle align in the direction below the horizontal, and hence you have defined a term angle of dip. If the same would have been done in the southern hemisphere, then it would have been called angle of rise. The angle by which the Earth magnetic field rises above the horizontal. Now, angle of dip is the angle made by Earth's magnetic field with the horizontal. Now, let's say this is the net Earth's magnetic field at a place where the angle of dip is delta. Sir, is the angle of dip same everywhere? No. We know that at the magnetic north pole, the direction of Earth's magnetic field is downward. So at the magnetic north pole, the angle of dip is 90 degree, right? Now, we can break down this Earth's magnetic field into component, vertical component and horizontal component. The vertical component of this Earth's magnetic field will be nothing but B sine delta. If the angle of dip is delta, which is the angle made by Earth's magnetic field with the horizontal, you should know how to take components. And the horizontal component is nothing but B cos delta. So at a place where the angle of dip is delta and the strength of Earth's magnetic field is B, the horizontal component is B cos delta while the vertical component is B sin delta. Now we need to understand what is the angle of dip at different position on Earth. First of all, remember that it's called angle of dip. Why it's called angle of dip? Because the entire development of science took place in the northern hemisphere, and in the northern hemisphere the magnetic needle always dips. So in northern hemisphere the angle of dip is taken as positive because in the northern hemisphere the needle actually dips. In the southern hemisphere, the angle of dip is negative because in the southern hemisphere, the needle doesn't dip, the needle rises up. At magnetic north pole, what will be the value of angle of dip? So we know that when a person stands at the magnetic north pole, at the magnetic north pole, the Earth's magnetic field lines appear to enter into the Earth. So the direction of Earth's magnetic field is downward, and we take the angle of dip as plus 90 degree. If you are standing at the magnetic south pole is somewhere near the actual south pole. If you are standing at the magnetic south pole, then that's from where the Earth's magnetic field line appear to be coming out of the Earth. And you will say that at magnetic south pole, the direction of Earth magnetic field is up. So the needle will align up. But for rises, you take the angle of dip as negative because its name is angle of dip. So you will say that at magnetic south pole, the angle of dip is minus 90 degree because it's not at all dipping, it is rising. Do remember that at magnetic equator, the Earth's magnetic field line are parallel to the surface of Earth. Since Earth's magnetic field lines are parallel to the surface of Earth, we say that if a needle is suspended, it will align parallel to the surface of Earth in the horizontal direction, and hence at the magnetic equator the angle of dip has to be 0. These are the important points that a child should know about angle of dip. The next thing we are going to talk about is called the angle of declination. Now what is the meaning of angle of declination? Why do we use a compass to navigate? To navigate on Earth, you need to know the position of geographic north. Yes. But the compass needle points towards magnetic north. No doubt the magnetic north is close to geographic north. And still the compass needle do a good justification to the navigation. But it's not accurate. So as to use it accurately, we should know that at any place on Earth, how much the compass needle is telling us the wrong. For example, the compass needle, let's say in the front of Earth, if you are sailing, points towards the magnetic north. But you are using the compass needle for navigation. So you need to know what is the direction of actual north. Think 3D, I'm drawing in 2D, but visualize it in 3D. So you are using compass needle for navigation, it will point towards the magnetic north, but you wish to go to the actual north. The angle by which this reading is wrong, you can call that angle as the angle of declination. So if you are using a compass needle to navigate on the surface of Earth, the compass needle has nothing to do with your geographic north. The compass needle will point towards magnetic north, and the deviation produced by this phenomena is called the angle of declination. So let's understand it once more. A compass needle points towards the magnetic pole, not at all towards the geographic pole. To utilize the compass for navigation, we need to know the angle between the north shown by the compass needle and the actual north. If the compass needle points this way, it will always point towards the magnetic north, and you are using it to reach the geographic north, right? So to utilize the compass for navigation, we need to know the angle between the north shown by compass and the actual north, because we are moving on the surface of Earth. This angle is known as angle of declination. That is the angle between the direction of north as shown by a compass needle and the actual north. The angle between them is called the angle of declination. So do understand that if at a place on earth the compass needle points this way, it points towards the magnetic north. Understand that the direction of horizontal component of earth's magnetic field is in the direction where the compass needle points. The direction of horizontal component of earth's magnetic field is in the direction the compass needle points. So, the angle made by horizontal component of Earth's magnetic field with the true north is called angle of declination, and this definition is the one which will be really useful in solving questions. I tell students not to go by the definition which is given in every book, but you should know what is the true definition. The true definition of angle of declination goes something like the angle between the magnetic meridian and the geographic meridian is called angle of declination. The angle between the magnetic meridian and the geographic meridian is called the angle of declination. But believe me, this definition gives you no visualization of what the angle of declination is. So sir, what should I remember the angle of declination to be? Remember that the angle made by horizontal component of Earth's magnetic field with the true north. So if let's say the horizontal component of Earth's magnetic field is here, and the direction along which you have to move to reach the north pole of Earth is here, the angle between them is called the angle of declination, and the symbol we are using for declination is theta. The symbol we used for angle of dip is delta. Now we need to understand one more thing about the angle of declination. Let's say this is our Earth. We know that this is the geographic axis, and this point is geographic north pole, and the magnetic north pole is at some deviation from the geographic north pole. So this is magnetic north. North as shown by a compass needle. This is geographic north. Now let's say somebody is standing on the front part of Earth. Somewhere here, near the equator. For this person, the compass needle will point towards, so the compass needle points in direction of magnetic field, and the magnetic field lines of Earth will be towards magnetic north, so the compass needle will point towards the magnetic north. But you are using it for navigation, so you need to know the angle between the direction of north as shown by compass needle and the true north, and the angle between them will be called the angle of declination. Now let's say you started moving from the equator towards the pole. So now you have reached this point. On reaching this point, again the compass needle will point in direction of Earth's magnetic field. That will be towards the magnetic north. But you are using the compass needle to go towards the actual north. So now the angle of declination will be this angle. You keep on moving towards the pole. Better think 3D. On the surface of Earth, on the surface of sphere, you are moving from equator towards the pole. So now, if you keep on moving up towards the pole, and let's say you have reached this point, and you are still using the compass needle to navigate, you will find that now the compass needle again points towards the magnetic north, but you are using it to go towards geographic north, and now the angle of declination is even larger. So remember this statement, as we move from equator to pole, the angle of declination increases. Here you can see less declination, less deviation in the reading. Here you can see more deviation, here even more deviation. That's why the sailors always used the compass needle nearby the equator, because in this region nearby the equator, the deviation in the reading shown by the compass needle is less because the declination is less, and nearby pole the declination is large. So as we move from equator to pole, the declination increases. You need to remember this for all question solving purposes. Remember the line, the angle of declination is the angle made by horizontal component of Earth magnetic field with the true north. So now we will talk about dip circle. The name itself says dip circle, the device which is used to measure the angle of dip. And what is the angle of dip? Angle of dip is the angle made by Earth's magnetic field with the horizontal. So in a dip circle, we have got an instrument which looks like this. In this instrument, you can see that there is a vertical plane, and on this vertical plane, we have placed a magnetic needle. And there are markings on this vertical plane so that we can know what is the angle made by the magnetic needle at a particular orientation. This vertical plane can be rotated about a vertical axis passing through its center. So this vertical plane can be turned, and there is a horizontal scale placed under it to measure how much the vertical plane has been turned, by how much angle it has been rotated. To understand dip circle, you need to understand the following things. The first, a magnetic needle is free to rotate in the vertical plane. So this magnetic needle can rotate in the vertical plane. Why? Because the plane is vertical. So if you have got this vertical plane, no matter what orientation you keep it in, if you hinge a magnetic needle to it, then this magnetic needle is free to rotate in the vertical plane. So it can rotate like this. It will point in the direction of net magnetic field, or it can rotate like this, but it will point in the direction of net magnetic field in the plane. Now to understand dip circle, you need to be very careful in understanding the next 2 points which I am going to say. So if a magnetic needle is hinged on a plane, if the magnetic needle is hinged on a plane, you take a plane, you take a magnetic needle and you hinge it. Okay, if a magnetic needle is hinged on a plane, then these 2 points are important. The first point, a magnetic needle will align in the direction of net magnetic field in the plane. A magnetic needle will align in the direction of net magnetic field in the plane. So let's say you have got this plane and you have hinged a magnetic needle over it. Now this magnetic needle is free to rotate in the plane, right? Now let's say if the net magnetic field in this plane is towards you guys, then this magnetic needle will point towards you guys. If the net magnetic field in this plane is towards east, then this magnetic needle will point towards east. If the net magnetic field is towards me, it will point towards me. But sir, what if the net magnetic field is downward? Can this needle which is hinged point downwards? No. So what will it do? It will do nothing. So the second point comes from here. There is no effect of the magnetic field perpendicular to the plane. So if you take a magnetic needle and hinge it on a plane, then the magnetic needle will align in the direction of net magnetic field in the plane, and there will be no effect of magnetic field perpendicular to the plane. To understand this better, let's understand a real world example. A compass needle free to rotate in horizontal plane, a compass needle which is free to rotate in horizontal plane. It can't rotate along a vertical plane. A compass needle free to rotate in horizontal plane. If taken at magnetic poles, sir, what are magnetic poles? The north magnetic pole and south magnetic pole. At the location of north magnetic pole, the direction of earth magnetic field is downward. At the location of south magnetic pole, the direction of earth magnetic field is upward. So if you take this compass needle which is free to rotate in the horizontal plane at the magnetic poles, then in which direction it will point? Sir, if you have taken it to magnetic poles, let's say north magnetic pole, the direction of earth magnetic field is downward. If the direction of earth magnetic field is downward, it won't budge. It won't change its orientation. So if placed at magnetic poles, points in any random direction, it won't point in the direction of magnetic field. Why? Because there is no effect of magnetic field perpendicular to the plane. So just remember this point. When you have got a magnetic needle hinged on a plane, then the magnetic needle will align in the direction of net magnetic field in the plane, and there will be no effect of magnetic field perpendicular to the plane. Now let's understand how do we correlate the apparent angle of dip, that is the angle of dip measured by a dip circle, with the actual angle of dip at a place. Let's say we have placed the vertical plane of the dip circle such that it makes an angle theta with the magnetic meridian. It makes an angle theta with the magnetic meridian. But rather than using the word magnetic meridian every time, I will say that let's say we have got this dip circle whose vertical plane has been placed at an angle theta with the horizontal component of Earth's magnetic field. So if we look from the top and the dip circle's plane, when look, the dip circle's vertical plane is a circle, right? But when look from top, it will look like a straight line. So let's say you have got the plane of the dip circle, the circular plane, placed at an angle theta with the horizontal component of Earth's magnetic field. Now we can break down this horizontal component of Earth's magnetic field into two components. We will say that the component of this horizontal component of Earth's magnetic field in the plane of the dip circle will be nothing but the horizontal component of Earth magnetic field into cos theta. And we can say there will be one more component of this horizontal component of Earth's magnetic field that will be perpendicular to the plane. And that component of Earth's magnetic field perpendicular to the plane will be BH sine theta. So break down the horizontal component of Earth's magnetic field into two components. One in the plane of the dip circle. Second, perpendicular to the plane of the dip circle. Do understand that if there is a horizontal component of Earth's magnetic field, then there also have to be a vertical component of Earth's magnetic field. So let's say we have got this downward component of Earth's magnetic field BV. So think that we have placed the plane of the dip circle at an angle theta with the horizontal component of Earth magnetic field. We have broken down the horizontal component of Earth magnetic field into two components, one in the plane, another perpendicular to the plane, and there is a vertical component of Earth's magnetic field. Now, if we look from the side, rather than looking from top, if we look from the side, what will the side view look like? So when seen from the side, you will observe the dip circle. It has got marking over it. There is a component of the horizontal component in the plane of the dip circle, and this component is BH cos theta. There is a vertically downward component of Earth's magnetic field which is also in the plane of the dip circle. So what will be the vertical component? We know that if the Earth's magnetic field makes an angle delta with the horizontal, that angle delta is called the angle of dip. The vertical component of Earth magnetic field is nothing but B sine delta, while the horizontal component is nothing but B cos delta. And this BH cos theta is the component of that horizontal component in the plane of the dip circle. So we also have a vertical component, and that vertical component is BV. Now the magnetic needle will align in the direction of net magnetic field in the plane of the dip circle. Now the net magnetic field in the plane of the dip circle will be somewhere here because of the resultant of BV and BH cos theta. So the needle will align somewhere here, and let's say this angle made by the magnetic needle with the horizontal is the apparent angle of dip. So we can say that the vertical component is BV, the horizontal component is BH cos theta, and the net magnetic field makes an angle delta apparent with the horizontal. So we will say that the apparent angle of dip equals to BV by BH cos theta, vertical upon horizontal. Now you can write this BV by BH as tan delta, because we know that if the Earth's magnetic field B makes an angle delta with the horizontal, which is the angle of dip, then this tan delta can be written as BV by BH. So in place of BV by BH, you can write tan delta, and you will get tan delta apparent equals to tan delta by cos theta, and this is something you have to mug up, and if you mug up this, you will get all your marks on any question based on dip circle. So let's understand this formula slowly. So what is tan delta apparent? Tan of the apparent angle of dip. So what is the apparent angle of dip? Apparent angle of dip is the angle of dip as measured by a dip circle. So what is tan delta? Tan of the actual angle of dip at that place on Earth. And what is cos theta? Beta, theta is the angle made by the plane of the dip circle with the magnetic meridian, or theta is the angle made by the plane of the dip circle with the horizontal component of Earth's magnetic field. Even if you haven't understood any part out of here, do not worry, just remember this formula and all your problems will be solved. So tan delta apparent equals to tan delta by cos theta, game over. Tan delta apparent equals to tan delta by cos theta, game over. Now bachcho, we can say that delta apparent is the apparent angle of dip, delta is the actual angle of dip, and theta is angle made by the plane of the dip circle with the magnetic meridian, or theta is the angle made by the plane of the dip circle with the horizontal component of Earth's magnetic field. So just remember this formula right here, right now, and all questions you will be able to answer. Now, based on this formula, we can conclude many things. So let's start concluding them. We know that tan delta apparent equals to tan delta by cos theta. What is delta apparent? Delta apparent is the apparent angle of dip as measured by a dip circle. What is delta? The actual angle of dip at that location. What is theta? The angle made by the vertical plane of the dip circle with the magnetic meridian or with the horizontal component of Earth's magnetic field. Now, beta, the first thing, delta apparent equals to actual angle of dip. For the apparent angle of dip to be same as the actual angle of dip, for delta apparent to be equal to the true angle of dip, you will say that cos theta has to be equals to 1. And when cos theta equals to 1, it means that theta equals to 0. It means that the apparent angle of dip is same as the actual angle of dip when the vertical plane of the dip circle is placed in the magnetic meridian. So that the angle between the vertical plane of dip circle and the horizontal component of Earth's magnetic field is 0. So you say that the apparent angle of dip is same as the actual angle of dip when the dip circle has got its plane placed in the magnetic meridian, so that the theta becomes 0. The second point is, as the magnitude of cos theta is always less than or equal to 1, you can write tan delta apparent equals to tan delta by cos theta. And this denominator will always have magnitude less than 1. Since denominator will always have magnitude less than 1, you can say that tan delta apparent always have to be greater than equal to tan delta. It becomes equal when cos theta is 1. That is when theta is 0. That is when the vertical plane is placed in the magnetic meridian. So you will say that tan delta apparent is always greater than equal to tan delta, or you will say that the apparent angle of dip always have to be greater than equal to actual angle of dip. So if you place the dip circle at a place where the actual angle of dip is, let's say, 30 degree, then the apparent angle of dip must have magnitude more than 30. It can be 45, it can be 50, it can be 60, it can be 90, but it can't be 15 degree. So you can't have apparent angle of dip, that is the angle of dip measured by the dip circle, to be less than the actual angle of dip. It has to be more. The next point goes like, for theta equals to 90 degree. This means that when the plane of the dip circle is perpendicular to the magnetic meridian, or when the plane of the dip circle is perpendicular to the horizontal component of Earth's magnetic field, then if you substitute here theta equals to 90 degree, cos 90 becomes 0. So you get tan delta apparent equals to tan delta actual upon 0. So tan delta apparent becomes equals to infinity, and if tan delta apparent equals to infinity, it means that delta apparent has to be 90 degree. So you will say that for theta equals to 90 degree, cos theta is 0, and delta apparent has to be equals to 90 degree. It means that the needle of the dip circle will point down or it will point up depending upon in which hemisphere you are. If you are in northern hemisphere, then the Earth's magnetic field has a downward component. If you are in southern hemisphere, then the Earth's magnetic field has a vertically upward component. So if you are in northern hemisphere and the vertical plane of the dip circle is placed perpendicular to the magnetic meridian, then the needle points vertically downward due to the vertical component of Earth's magnetic field, and you will say that the angle of dip apparent using the dip circle is nothing but 90 degree. Now comes the next point. If for two perpendicular orientation of dip circle, the apparent angle of dip is delta 1 and delta 2, then what is the correlation between the apparent angle of dip and the actual angle of dip? And this is a question that has been asked by NEET already. So now here, let's say for two perpendicular orientation of dip circle, let's say this direction represents the horizontal component of Earth's magnetic field. You have placed the vertical plane of dip circle in two perpendicular orientations. So let's say first time the plane makes an angle theta, with the horizontal component of Earth magnetic field. In the second orientation of the dip circle, the angle made by the plane of dip circle has to be perpendicular to the first orientation. It means that the angle made with the horizontal component of Earth magnetic field will be 90 minus theta. Now, for these two orientation, you are getting the apparent angle of dip to be delta 1 and delta 2. So you will say that tan delta 1 equals to tan delta by cos theta. Yes. Substituting in place of theta, 90 minus theta for the second orientation, you will write tan delta 2 equals to tan delta upon cos of 90 minus theta. That becomes sin theta. Yes, sir. So, bachcho, from here, you can say that cos theta equals to tan delta by tan delta 1 and sin theta equals to tan delta upon tan delta 2, and we know that sin square theta plus cos square theta equals to 1. So tan square delta upon tan square delta 1 plus tan square delta upon tan square delta 2 equals to 1. Take this tan square delta common and bring it on the right hand side, so you get 1 upon tan square delta 1 plus 1 upon tan square delta 2 equals to 1 upon tan square delta. And this gives you 1 upon tan square delta 1 becomes cot square delta 1, 1 upon tan square delta 2 becomes cot square delta 2, and 1 upon tan square delta becomes cot square delta. So if for two perpendicular orientation of dip circle, you get the apparent angle of dip to be delta 1 and delta 2, then cot square delta 1 plus cot square delta 2 equals to cot square delta. This is something that you have to remember. So if for two perpendicular orientation of dip circle, if the apparent angle of dip is delta 1 and delta 2, then the correlation between the apparent angle of dip delta 1 delta 2 and the actual angle of dip delta is given by cot square delta 1 plus cot square delta 2 equals to cot square delta. So now let's start the easy part, that is bar magnet. So we all have seen and played with a bar magnet. We have identified two poles to a bar magnet, a north pole and a south pole. And here we say the same thing that we have said about charge, that like charges repel, so like poles repel and unlike poles attract. So if you place one more bar magnet near it, such that its south pole is closer to the first bar magnet south pole, so they will repel each other. And if you place one more bar magnet near it, such that its north pole is closer to the south pole of the first bar magnet given, then they will attract each other. So like poles repel, unlike pole attract, more or less kind of charges. And same thing is what physicists thought for a long frame of time. They observed the field lines created by this north and south pole, and they identified that the magnetic field lines originate at the north pole and terminate at the south pole. Was this true? Not at all. Do north pole and south pole exist? Not at all. But for a long time, physicists tried to keep it identical to the study of electrostatics. In the study of electrostatics, we have learned that the electric field lines originate at positive charge and terminate at the negative charge, right? So if the electric field lines originate at positive and terminate at negative, they use the same concept even for bar magnet. They say that we should treat the north as a positive pole and south as a negative pole, and the magnetic field lines are coming out of north and they are going towards the south. But this is what is observed outside the bar magnet, because we can look only in the region outside the bar magnet. In actuality, inside the bar magnet, magnetic field lines are from south to north. Magnetic field lines form a closed loop. Electrostatic field lines originate at positive and terminate at negative. So remember these points. The first point, outside the bar magnet, the direction of magnetic field is from north to south. Second point, inside the bar magnet, the direction of magnetic field is from south to north. And the third point, magnetic field lines form a closed loop. So these are the 3 points that you should know. Now let's talk about magnetic poles. So the physicists observed that, okay, when you have got this bar magnet and a second bar magnet, if connected from one side, if they repel, then connecting on other side, they attract, as if they are showing properties same as charges. They said that we will treat the North Pole as positive pole strength and we will treat the South Pole as the negative pole strength. But these North Poles and South Poles are not found exactly at the end of the bar magnet. They are found at some distance inside from the ends of the bar magnet. So let's say if we have a bar magnet of length L, the North Pole is thought to be same like of positive charge. So it is said to have a positive pole strength. While the South Pole is treated like a negative charge, it has a negative pole strength. The North Pole and South Pole are not found at the end, they are found at distance L by 12 inside from the ends. While teaching you this, I again want to place a disclaimer. North Pole and South Pole do not exist. It's just that physicists love to correlate things. So for a long time, they kept on correlating magnetism with charges, and all this theory is wrong. So moving on, the effective length of a bar magnet should be taken as the actual length minus L by 12 minus L by 12. That is the separation between the North Pole and the South Pole. And this L minus L by 12 minus L by 12 gives you L minus L by 6. That gives you 5L by 6. So if you have a bar magnet of length L, then the separation between the two poles of the bar magnet is 5/6 of the length of the bar magnet. Now do understand these points. It is not possible to have isolated monopole. You can never ever do this that you have got only South Pole. Poles always exist in pair. So if you find a crystal, if it has got North Pole, it will always have South Pole. You just can't have a monopole. Just like you can have isolated positive charge or negative charge, you can't have isolated monopole. Why? Because they do not exist. It's a rubbish statement. Second thing, bachcho, we treat North Pole as positive charge. So do we treat North Pole as positive charge? If you open up any current university level book that is taught in the colleges, there you won't find the term magnetic pole written in it. Why? Because they do not exist. But it's written in NCERT, so we have to learn about it. So we treat the North Pole as positive charge. We treat the South Pole as negative charge. So North Pole is treated as positive charge. The South Pole is treated as negative charge. So North Pole is said to have a positive pole strength, while the South Pole is said to have a negative pole strength. If you have got two monopoles of pole strength M1 and M2 separated by some distance r, then what will be the force between them? Physicists were constantly trying to correlate magnetism with charges. If you have got two charges Q1 and Q2 separated by distance r, then we know that the Coulombic force between them is given by K Q1 Q2 upon r square. Do monopole exist? No. But they already correlated it so much and predicted that Coulomb's law should work even for monopoles which do not exist. So they said that somehow, if in a hypothetical universe, we can find out two monopoles of monopole strength M1 and M2 and separate them by distance r, then if they are like, they will repel. If they are unlike, they will attract, and the force between them will be nothing but C M1 M2 upon r square. So here you have got K, here you have got C, here you have got charge, here you have got pole strength, here you have got distance between the charges, here you have got distance between the monopoles. And just like K in the K Q1 Q2 upon r square is 1 by 4 pi epsilon naught, this C in C M1 M2 upon r square is nothing but mu naught by 4 pi. So remember that this C is nothing but mu naught by 4 pi. Sir, if monopole does not exist, why are you teaching us this? Because beta, hypothetical questions are made out of this and they are asked in competitive examination. That's why you should know. And it's same as electrostatic. No worry. Second thing, we know that if we have a charge Q placed in an electric field E, then the force acting on the charge Q is given by QE. They developed the same theory for monopole. If you have a monopole of monopole strength M placed in a magnetic field B, then the force acting on this monopole will be MB. If it is a positive monopole, north monopole, it will have force in the same direction as magnetic field. If it is a negative monopole, a south monopole, then it will have force in direction opposite to magnetic field. So they gave this another formula already. that F equals to mb. Similarly, there is one more formula. We know that if we have a charge q, then the electric field due to this charge q at distance r is given by kq upon r square. Similarly, they said if we have a monopole of monopole strength m, then at a distance r from it, the magnetic field produced by it will be nothing but Cm by r square. In place of k, C in place of q, m. That's all. Now, bachcho, they said even the same thing they say for charges. A positive charge produces field away from it. So a north pole, a positive pole strength produces magnetic field away from it, while a negative pole strength produces magnetic field towards it. Same type of formula, nothing to worry. Anyways, all these concepts are outdated. Monopoles do not exist. North and south pole do not exist. So now we will talk about magnetic dipole moment. We have learned that if we have got a pair of equal and opposite charges, they form a dipole. And the dipole moment for this pair of charges is defined using the symbol P, and P equals to QR, where R is the position vector of the positive charge with respect to negative charge. Similarly, every time we have a bar magnet, we think of the north as the positive pole strength and the south as the negative pole strength. And we have defined the magnetic moment of a bar magnet in the same way we define the dipole moment of a dipole. We say that the magnetic moment of a bar magnet is nothing but pole strength times the position vector of positive pole strength, which is the north pole, with respect to the negative pole strength, which is the south pole. So the magnetic moment of a bar magnet equals to magnetic pole strength multiplied by the position vector of the positive pole, which is the north pole, with respect to the negative pole, which is the south pole. So remember this. What is R? R is the position vector of positive pole with respect to the negative pole. That's how easy it is. Now let's practice some question on combination of bar magnets. For example, you get this type of question. Here they will say that we have got two identical bar magnets, each of magnetic moment m, and they are placed in the fashion shown in the figure. The angle between the two bar magnets is 60 degrees. You need to determine the resultant magnetic moment of the system if each bar magnet has a magnetic moment m. So here, rather than thinking of the bar magnet, think of the magnetic moment vector. For this first bar magnet, you will say that the magnetic moment is from south to north. For the second bar magnet also, the magnetic moment is south to north. And both of them have the same magnetic moment m and m. So you will say that the equivalent magnetic moment will be under root of m square plus 2 into m into cos of the angle between the vectors. And the cos of this angle, 60 degree, will be nothing but half. So once you substitute this, just 2 and 2 get cancelled. So what you get is under root of m square plus m square plus m square. That is under root of 3m square. That gives you root 3m. So for this case, the equivalent magnetic moment of the system of these two bar magnets will be root 3m. Let's think of another example. If the two bar magnets are placed like this, now what will be the magnetic moment? The common error that students do here is that they think that the angle between the two magnetic moment vectors is 60 degrees. No, that's not at all the case. Remember that the angle between two vectors is the angle between them when they are joined tail to tail. So think of the first bar magnet, it has some magnetic moment m. Think of the second bar magnet, it also has magnetic moment m. Now to find the equivalent magnetic moment, join the two bar magnets in tail to tail fashion. Now tell me what is the angle between these two bar magnets, or what is the angle between the magnetic moment of these two bar magnets. So you will say that this angle is 120 degree. So when you find the equivalent magnetic moment using the formula for addition of two vectors, you will get under root of m square plus 2 into m into cos 120. And we know that cos 120 is minus half. So what you get is under root of m square plus minus m square. So that gives you root of m square, which is nothing but m. So for this case, as the angle between the two magnetic moment vectors is not 60 degree, it is 120 degree. The equivalent magnetic moment comes out to be m. If they give you this case, now what will be the equivalent magnetic moment for these four bar magnets? So rather than thinking of bar magnet, think of four vectors. So first vector of magnetic moment M, south to north. Second one, magnetic moment M, south to north. Third one, magnetic moment M, south to north. Fourth one, magnetic moment M, south to north. Now you can see that these two vectors will cancel out each other. So your equivalent magnetic moment will be due to these two vectors pointing in the same direction. So you will say that the M equivalent for this case will be nothing but 2M, as these two bar magnets cancel out each other's magnetic moment, while the magnetic moment of these two bar magnets add up as they are in the same direction. So the equivalent magnetic moment comes out to be 2M. Now let's think of one more case when you again have got these four bar magnets. Do understand that the direction of magnetic moment is from south to north. So for this one M, for this one M, for this one M, for this one M. So you can see that both these magnetic moments are in same direction. So in the vertical direction you will get a net magnetic moment of 2M, and both these magnetic moments are also in the same direction. So in horizontal direction also you will get a net magnetic moment of 2M. So the resultant magnetic moment will be root 2 times that of individual. So the resultant magnetic moment will be nothing but root 2 times of 2M. This is nothing but basic vector addition. So the magnetic moment is 2 root 2M for the system of these four bar magnets. Now we will talk about cutting of a bar magnet. So let's say you have got this bar magnet and you are cutting the bar magnet perpendicular to its length. So if this is the bar magnet, you are cutting it perpendicular to the length. So here or somewhere here. Now let's say we have got this bar magnet in which the north pole has pole strength plus M, the south pole has pole strength minus M, and we have cut it into two pieces. Now cutting the bar magnet into two pieces doesn't make that you have got now only here north pole plus M and now here only south pole minus M. Monopoles do not exist. So what you get is two smaller bar magnets. And do understand that these smaller bar magnets have the same pole strength as the bigger bar magnet. So sir, if the bigger bar magnet has got pole strength plus M and minus M, then each of these smaller bar magnet will have the same pole strength plus M and minus M. Yes. So what if I divide it further? Then again you will get even two smaller bar magnets having the same pole strength plus M and minus M. So sir, cutting the bar magnet perpendicular to its length, the pole strength do not change. Yes. Okay, if you say so. So remember that when you cut the bar magnet perpendicular to its length, the pole strength remains the same. But beta, just like when you have a dipole, you get the electric field at a point due to what? The charge or due to the dipole moment. We write that at an axial point, the electric field comes out to be 2 kp by r cube. Electric field produced by an electrical dipole depends upon the dipole moment. Similarly, when you have a magnetic dipole of dipole moment M, then at an axial point, the magnetic field produced by it comes out to be 2cm by r cube, where beta c is mu naught by 4 pi. And at an equatorial point, the magnetic field is in the direction opposite to dipole moment, and the magnetic field is equals to cm by r cube. Here beta m is not the pole strength, here m is the dipole moment. So how strong the electric field will be produced by a bar magnet depends upon its magnetic moment, not on its pole strength. So remember that when you cut a bar magnet perpendicular to its length, the pole strength remains the same. But do understand that now, since for one individual bar magnet compared to the original, the separation between the poles has decreased. As the separation between the poles has decreased, you will say that the magnetic moment of the bar magnet decreases. And if, when compared to the bigger original bar magnet, one smaller piece has got lesser magnetic moment, it will produce weaker magnetic field, because the magnetic field produced by a dipole depends upon dipole moment and not on the charge. So you will say, as the length decreases, each small part has a smaller magnetic moment. Sir, why? I just said, no, if you have got a bar magnet You have got south pole, negative pole strength, north pole, positive pole strength. You write the magnetic moment as m times the position vector of positive pole strength with respect to negative pole strength, right? So beta, here, since the separation between the poles decreases, r decreases, so the magnetic moment decreases, so the magnetic field produced by this smaller piece will be weaker. What remains same is the pole strength. The magnetic moment no doubt decreases. Moving on to the next case. If we cut the bar magnet along its length, so if you have a bar magnet and you are cutting the bar magnet along its length. So do understand that when you cut the bar magnet along its length, then you get pieces of smaller cross-sectional area. So if the original bar magnet has a cross-sectional area A, the smaller piece will have a lesser cross-sectional area. Now let's say this piece formed now has a cross-sectional area A dash. Do understand that the magnetic pole strength is directly proportional to cross-sectional area. If let's say you have a bar magnet of cross-sectional area A and you cut it into two identical pieces, while cutting it parallel to the length, then each of the smaller piece formed will have half the cross-sectional area. So one of the piece will have a cross-sectional area A by 2. Do understand that the pole strength is directly proportional to cross-sectional area. So if the bigger bar magnet, the complete bar magnet, has got pole strength plus m and minus m, then when the cross-sectional area becomes half, the smaller piece will have half the pole strength plus m by 2 and minus m by 2. So when you cut the bar magnet along its length, the cross-sectional area decreases. Since the cross-sectional area decreases, the pole strength decreases. So here remember that as on cutting along the length, the cross-sectional area decreases, the pole strength decreases. As the pole strength decreases, you say that the magnetic moment will decrease because still the separation between the two poles is same. And we know that magnetic moment can be thought of as the pole strength times the separation between the poles. When you cut along the length remains the same, but the pole strength decreases, so the magnetic moment decreases. Hence, this bigger bar magnet will have a higher magnetic moment. It will produce a stronger magnetic field, while this piece will have lesser magnetic moment and it will produce a weaker field. This is something which is usually not taught by teachers, but I want you to remember it this way. Remember that the magnetic moment of a bar magnet is directly proportional to its volume, and I will teach you about this in the next hour. But remember that the magnetic moment of a bar magnet is directly proportional to its volume. So if you cut the bar magnet in such a way that the volume of one of the piece is half that of total, then its magnetic moment will be half. If you cut it in such a way that its volume is 1/3 that of total, then its magnetic moment will be 1/3 that of total. Remember that the magnetic moment of a bar magnet is directly proportional to its volume. Now let's say you have got this bar magnet and you have cut it into two pieces and you have cut it perpendicular to the length. If the original bar magnet has magnetic moment m and you cut this bar magnet of length L into two pieces, one of length L by 3, one of length 2L by 3. You need to tell me what will be the magnetic pole strength of one of the smaller piece of, let's say, length L by 3 after cutting. So sir, you have cut perpendicular to length, no? So the pole strength will remain the same. Next question, if this bigger bar magnet has a magnetic moment m, what will be the magnetic moment of this smaller piece after cutting? So sir, see, pole strength is same and the separation between the poles becomes 1/3. So using the formula that magnetic moment equals to pole strength times separation between the poles, as the separation between the poles becomes 1/3, magnetic moment will become 1/3. Yeah. So now this smaller piece will have 1/3 of the total magnetic moment m by 3, and this bigger piece will have 2/3 of the total magnetic moment. Do understand that magnetic moment is directly proportional to the volume of the bar magnet. On cutting it this way, this smaller piece will have 1/3 the volume of the total. As it has 1/3 the volume of the total, it will have 1/3 the magnetic moment. And this larger piece has 2/3 the volume of the total, so it will have 2/3 the magnetic moment. So the magnetic moment of this 1/3 length will be m by 3, and magnetic moment of this 2/3 length will be 2m by 3. Sometimes this type of question is asked. You have a bar magnet. You are not cutting it along the length. You are not cutting it perpendicular to the length. If I cut this bar magnet of magnetic moment m this way, now what will be the magnetic moment of one of the pieces? This question can be answered only thinking that magnetic moment of a piece is directly proportional to its volume. When you cut it this way, one of the piece will have half the volume of the total. If total has a volume V, then one of the piece here will have a volume V by 2. And if the volume becomes half, then bachcho, the magnetic moment becomes half. So this upper half piece after cutting will have a magnetic moment m by 2, and the lower half piece also after cutting will have a magnetic moment m by 2. What if you have a bar magnet of cross-sectional area A and length L, which you cut into 4 pieces this way? You make a cut perpendicular to length at a distance L by 3 from one end. So the remaining 2 parts will have length 2L by 3, and you cut it along the length also, such that 1/3 of cross-sectional area is in the upper part and 2/3 of the cross-sectional area is in the lower part. So after making these 2 cuts, you will have 4 pieces. The first piece, the second piece, the third piece, and the fourth piece. Question is, if the bigger bar magnet has a magnetic moment m, can you tell me the magnetic moment of each one of these 4 smaller bar magnets? So you will say that the magnetic moment is directly proportional to volume. The whole complete bar magnet has a volume, cross-sectional area A into length L, AL. Now let's look at volume of this first piece. So for this first piece, you will say that the cross-sectional area is A by 3, yeah. The length is L by 3, yes. So its volume will be AL by 9. A by 3 into L by 3, AL by 9. If the volume is 1/9 that of total, its magnetic moment will also be 1/9 that of total. So if the whole bar magnet has a magnetic moment m, this small piece will have a magnetic moment n by 9. Now let's think of the second piece. For the second piece, you will say that the cross-sectional area is A by 3, while the length is 2L by 3. So its volume will be A by 3 into 2L by 3. That will be 2AL by 9. The whole bar magnet has a volume AL. This piece has a volume 2AL by 9. So if the volume becomes 2 by 9 times, the magnetic moment becomes 2 by 9 times. So this piece will have a magnetic moment of 2m by 9. And similarly, you can write down the magnetic moment of each part. So since this part has 1/9 the volume, cross-sectional area is 1 by 3, length 1 by 3. So its volume is 1/9, so its magnetic moment will be 1/9. This piece has 2/3 the cross-sectional area, 1/3 the length, so it has got 2 by 9 times the volume. If it has got 2/9 of the volume, its magnetic moment will be 2/9. Think of the other 2 pieces. This piece has a length of 2L by 3, cross-sectional area of A by 3, so its volume is 2 by 9 times of total. Since its volume is 2 by 9 times of total, its magnetic moment will be 2 by 9 times of total. And last, think of this piece. Its cross-sectional area is 2/3, its length is 2/3, so its volume is 4 by 9 times of total. Since its volume is 4 by 9 times of total, its magnetic moment will also be 4 by 9 times of total. That's all. So let's move on and talk about bar magnet placed in a uniform magnetic field. Here, in this case, I will repeat all the things which we have done already for an electrical dipole placed in a uniform electric field. Here we learned the first thing, that irrespective of the orientation of the dipole, the force on a dipole placed in uniform electric field is 0. The torque on electrical dipole is given by P cross E. The torque is maximum when the angle between the dipole moment vector and field is 90 degree, and this maximum torque comes out to be PE when theta equals to 90 degree. There are 2 orientations of the dipole for which the torque on the dipole is 0. This is theta equals to 0 and theta equals to 180 degree. We call theta equals to 0 as a stable equilibrium, and we call theta equals to 180 degree as unstable equilibrium. Stable equilibrium means that when displaced from the equilibrium position, the dipole tries to realign with the original equilibrium position. So theta equals to 0 is the position of stable equilibrium. That's why we say a freely suspended dipole always try to align itself in the direction of field. An electrical dipole always try to align in the direction of electric field. A magnetic dipole always try to align in the direction of magnetic field. So there is stable equilibrium, unstable equilibrium, and then we learned that the potential energy of dipole in a uniform electric field is given by minus P dot E. So let's do the same things but for a bar magnet. So if you have a uniform magnetic field which contains a bar magnet, think of a bar magnet as a magnetic dipole, direction from south to north. The net force acting on the dipole, magnetic dipole, irrespective of orientation, will be 0. The torque acting on this dipole will be given by, there in electric we write P cross E. Here bachon we write M cross P. What is M? The magnetic dipole moment. We know that the torque is maximum when theta equals to 90 degree, and this maximum torque will be nothing but M into B. So maximum torque is MB when theta equals to 90 degree. Same things we have done for electrical dipole, and all these points are important. Next bachon, we know that the torque is 0 for theta equals to 0 or theta equals to 180 degree, where 0 represents the position of stable equilibrium and 180 represents the position of unstable equilibrium. The potential energy of dipole placed in a uniform magnetic field is given by, there we have learned that the potential energy is given by minus P dot E. Here we write the potential energy equals to minus M dot B. Same concepts again. So what we need to remember is, for theta equals to 0, torque acting on the dipole is 0. The potential energy is minimum, and this minimum potential energy is minus MB. And this is the case of stable equilibrium. In case of stable equilibrium, the potential energy is minimum. The next case, for theta equals to 180 degree, when the magnetic dipole is anti-parallel to magnetic field, then you will say that for even that case, the torque acting is 0. The potential energy, substitute here in M dot B, 180. So you will get minus MB cos theta, and in place of theta substitute 180, you get minus MB cos 180, and beta cos 180 is minus 1, and minus minus becomes plus, so you get MB. So the potential energy comes out to be plus MB. And this is the case of unstable equilibrium. No doubt the torque is 0, force is 0, but this is the case of unstable equilibrium. Now the next thing we need to talk about is the torque acting on a dipole placed in a magnetic field. So we know that when we have a bar magnet in a uniform magnetic field, a torque acts on the dipole, right? And this torque tries to align the bar magnet in the direction of magnetic field. If we take the bar magnet from the position of stable equilibrium, that is when theta equals to 0 degree, and turn it from position of stable equilibrium by some angle and release it, what does it do? It starts oscillating about the position of stable equilibrium. We can find out the time period associated with this oscillatory motion. How? First of all, you need to understand that the type of oscillation this bar magnet will do won't be linear SHM, it will be angular SHM. Just like the necessary and sufficient condition for an SHM to be linear SHM is F equals to minus Kx. Similarly, the necessary and sufficient condition for a motion to be angular SHM is torque equals to minus C theta. So the torque should also be restoring in nature, and torque should be directly proportional to the displacement from the mean position. So we know that the torque acting when displaced by some angle theta is given by MB sin theta. And then you can say that for small value of theta, if you are displacing it by very small angle, for small value of theta, we know that we can approximate sin theta to be nearly equal to tan theta to be nearly equal to theta. But this thing works only when the theta is small and you take theta in radian, not in degree. Now, we know that for small value of theta, we can write torque to be nearly equals to mb theta, as sine theta will be nearly equal to theta. So torque equals to mb theta. Now compare it with the essential equation of angular SHM. For angular SHM, the necessary and sufficient condition is torque should be restoring in nature and torque should be directly proportional to theta, and the proportionality constant is c. Just like for linear SHM, we know that the time period equals to 2 pi under root m by k. For angular SHM, the time period comes out to be 2 pi under root of I by c. So remember that for angular SHM, time period is 2 pi under root I by c. What is I? Moment of inertia. What is c? This restoring proportionality constant. So you will say that this c for a bar magnet oscillating is nothing but mb compared with torque equals to c theta. So c has to be nothing but mb. So the time period comes out to be 2 pi under root I by mb. So remember that the time period of oscillation of a bar magnet in a uniform magnetic field is given by 2 pi under root I by mb, and this thing works for a small oscillation. So that's all in this hour. In the next hour, we will talk about paramagnetic, diamagnetic and ferromagnetic materials. See you guys in the next hour. Bye bye. So that's all for now. See you guys in the next hour.